Hi students, in this first video for online lecture 3, we are now going to talk about isotopes. So what is an isotope? Well, first we need to start with some basic fundamental understanding of our subatomic particles. First thing that we're going to do is look at the atomic number. This is signified by the letter Z. This is the number of protons in the nucleus. This can be easily found on the periodic table as the number in the middle top of each elemental's box. So then we can look at the mass number, which is A. This is the number of protons plus the number of neutrons. This can be found by adding both of the subatomic particles in the nucleus together. We will show you how to calculate that. So finally, what is an isotope? Well, an isotope is the atom of the same element, which means it has the same atomic number, but has a different number of neutrons in their nuclei. If you change the number of protons, you will change the element. If you change the number of neutrons, but leave the number of protons the same, you will have an isotope. So let us go and look at a very nice notation. As you can see here, we have our elemental symbol. These can either be 1 or 2-letter abbreviations signifying what element you have. The mass number, A, which once again is the sum of the protons and the neutrons, is located in the upper left-hand corner. Our atomic number, Z, can be located in the lower left-hand corner. However, if we have the correct elemental symbol, this can be fairly redundant, and we will typically omit this. So here are 3 famous isotopes. First off, the most famous isotopes is the baseball team from The Simpsons, the Springfield isotopes, which then became the Albuquerque isotopes in real life. But let's go ahead and look at hydrogen. Hydrogen, as an element, has 3 isotopes. Hydrogen, as you know it, is hydrogen 1. This has 1 proton and no neutrons. If we go to hydrogen 2, commonly known as deuterium, it has 1 proton, as you can see here with our red proton, and 1 neutron. This was used in heavy water experiments during the creation of the nuclear programs, but by not only the Americans, but as well as the Germans during World War II. Finally, if you go to hydrogen 3, which we commonly call tritium, you will notice that it has 1 proton and 2 neutrons. So the reason why all 3 of these are considered hydrogen is because it has the 1 proton. To go from hydrogen to deuterium to tritium is going to be changing the number of neutrons. So once again, if you change the number of protons, you change the element. If you change the number of neutrons, you will get a different isotope. Here are 2 famous uranium isotopes. We have uranium-235 and uranium-238. It's very important to look at one big difference between these 2. Uranium-235 is what we know to be as a nuclear grade isotope. This is the one that we try to make nuclear weapons out of. Uranium-238 is actually fairly stable and does not radioactively decay as quickly as uranium-235. How we go and make good nuclear weapons, or what we typically call nuclear enrichment, is that the percentage of 238 is much larger. So we would go and take a very large sample of uranium, hoping to find more uranium-235. So now let's try this example. Give the number of protons, neutrons, and electrons for each of the following species. So let's go ahead and look at our sodium-20. Notice that it says we have sodium, and also notice that we can put the atomic number 11 located down and to the left. So this means that we are going to have 11 protons. So how many neutrons do we have? Well, now what we need to do is take our 20 subatomic particles in our nucleus and subtract the 11 protons to get the number of neutrons. If I do that, you will get 9 neutrons. So now the question becomes, how do I know how many electrons to have? Well, if it is a neutral atom, we must have as many electrons as we do protons. So in this case, you would end up having 11 electrons to balance the 11 proton charge. Let us go ahead and look at example B. Notice that I have the element identified, and I also have the mass number identified. So if I've correctly identified the element as gallium, this means that it is going to have 31 protons. Now if I go and take the mass number and subtract my 31 protons, I should end up with 40 neutrons. Seeing I have a neutral element, I am going to have 31 electrons to balance my 31 protons. So now we can go to oxygen 17. So in this case, I will have 8 protons. If I do 17 minus 8, I will get 9 neutrons. And because it is neutral, I will end up with 8 electrons. So the way that we can read these and have a better way of writing it into a paragraph is just writing the element and the mass number after it. You see it here as carbon-14. This is used to do isotopic carbon dating, and you will learn about this hopefully in your Chem 120 class. So carbon means that we have the elemental carbon, so this means that all carbon is going to have 6 protons. The 14 is the mass number, so that means that we are going to have 8 neutrons. And finally, if it is neutral, we will have 6 electrons as well. So this is a really nice way of being able to determine how many protons, neutrons, and electrons each of these isotopes have. Let's try this example. Given the number of protons, neutrons, and electrons, determine the atom or ion. So let's look at example A. Notice that I have the same number of protons and electrons. This means that I have a neutral element, so I will not expect to have anything with a charge. If I have 42 protons, this is going to be the element molybdenum, Mo. So now the only thing I really need to do here is add the subatomic particles that are in the nucleus, and that's by adding 42 and 57, and that will end up with 99. So the atom that I have for this example is molybdenum 99. So let's go to B. Notice that I have 34 protons, but 36 electrons. This means that I have more electrons than protons, meaning I will have a negatively charged ion. So the first thing I need to do is identify my atom. What has 34 protons? Well, that would be selenium. So this would be Se. If I go and put in my subatomic particles, I'm going to take the sum. So that would be a total of 75. But now I have to put the charge in to let us know that I have the ion and not the neutral atom. So because I have 2 more electrons, this would be 2-. This is the selenide 2- ion. For example, C, notice that I have more protons than I do electrons. So this means I'm going to have a positively charged ion. So if I look for the element with 37 protons, that is going to be rubidium. our element Rb. Well, if I have one more proton than electron, it is going to have a positive charge. And if I go and do the sum of my subatomic particles in the nucleus, we are going to end up having 79. So this is rubidium-79 plus ion. Let's go to our example D. Notice once again that I have more protons than electrons, so that means it'll be positively charged. If I have 28 protons, this means that I am going to have nickel. So that is nickel 2+. And then finally, I'm going to add my protons and neutrons together. So 28 and 32 happens to be the number of 60. So I would have nickel 60, 2+ ion. So what can this mean for all of us when we have different isotopes? Well, what we want to see is actually the abundance of these isotopes in real life. So the average atomic mass is a weighted average of all naturally occurring isotopes for an element. So when we look at our elemental symbols on the periodic table, the atomic number is listed in the middle at the top to tell you how many protons that element has. So as you can see with this example, for carbon, it has 6 protons. At the bottom, we will list our atomic mass. This is not going to be an integer value if there are multiple isotopes. So as you can see here, carbon has an average atomic mass of 12.01. The reason this is the case is that 98.9% of carbon is carbon-12. That would have a mass of 12 AMUs. But 1.1% of this carbon is also involved in our calculations. So this means that we must account for that. How we do this is by taking a weighted average like you see here below. If I have 0.9890 times 12 AMUs, that would be the abundance times the mass of my carbon-12, and add that to the abundance and the mass of my carbon-13. This is how you get this decimal form. If you have more than one isotope, these are calculations you have to know how to do. Some elements have 5, 6, 7, 8 different isotopes. This is a calculation that we will do further into the course. How this is actually done very easily for us is done by a technique called mass spectrometry. What happens during this case is that we are going to take a gaseous sample, bombard it with electrons, causing it to charge our element or compound we're putting in, and then we are going to put it through accelerating plates and then bend its path by a magnet. Now just imagine having a heavier car trying to make a turn versus a lighter sports car. So if we have a lighter sports car, it is going to bend it more and be able to move. And let's say that we have a very large semi-truck. It's not going to move and deflect much at all. So what this causes is our light species to be bent inward and go quicker and farther left on the detector. Our heavier species are going to be farther right on the detector because we can't deflect them as much. This is how we are able to separate species of different massless properties in a sample. So if we were to have, in this case, 3 different isotopes for neon, notice that there's a high percentage of the lighter isotope. There is a much smaller percentage of the heaviest isotope, and actually they were able to find a new isotope located between the two that could not be detected before without very good mass spectrometry detectors. So now what we need to do in this last example is determine the average mass for the following elements. This is your way of looking at the periodic table and being able to get the average atomic mass of our species. So let us go and first find the average atomic mass for tin. What is the atomic symbol for tin? Well, that is SN. So if we look at the periodic table, that mass would be 118 0.71 AMUs. So now for B, we can go and look for rhenium. This can be very tough because rhodium, ruthenium, and rhenium are located all very close to each other and have very similar periodic table symbols. If we find rhenium, you will find out that it actually has a mass of 186.21 AMUs. So let us go and find chromium. Chromium is a transition metal located in the first row of the transition metals, and it has a mass of 51.996 AMUs. So let's go to D and find francium. Francium is actually very unique because it is so short-lived that it's believed to have only one isotope. So anytime you look at the periodic table and you see that there are parentheses around a mass, that means that it is very short-lived, and that is the best estimate of the average mass of that specific element. So if I look at that, you will see that I end up getting a mass of 223 AMUs. Finally, if I go to my osmium, that is one of our heavier transition metals, and if I find it, you will see that I end up getting an average atomic mass of 190.23 AMUs. So as you see in this video, knowing all of our subatomic particles, how many and what element we have, becomes a very, very important thing for us as we begin our calculations while using various different elements. Have a great day.